In this video, we're going to cover section 1.12, complex reaction mechanisms. Reaction mechanisms are defined as the collection of individual kinetic processes or steps involved in the transformation of reactants into products. The rate law expression for a chemical reaction, including the order of the reaction, is entirely dependent on the reaction mechanism. For a reaction mechanism to be valid, the order of the reaction predicted by the mechanism must agree with the experimentally determined order. So let's consider the following reaction, where we have two equivalents of dinitrogen pentoxide reacting to give us 4 equivalents of nitrogen dioxide and molecular oxygen. Now, one possible mechanism for this reaction is that this is a single step consisting of a bimolecular collision between two N2O5 molecules. Now, a reaction mechanism that consists of a single elementary step, this is known as a simple reaction. And so in this particular example, the rate law predicted by this mechanism would be second order with respect to N2O5. Because if this were an elementary reaction step, we see that this is a bimolecular step and therefore second order with respect to that reactant. However, what's found experimentally is that this reaction is first order in N2O5 and not second order. Therefore, the single step mechanism shown here cannot be correct. So to explain the observed order dependence of the reaction rate, a more thorough or more complex reaction mechanism must be proposed. And this is the mechanism that's proposed for this particular reaction. We see we have 4 elementary reaction steps involved. We have N2O5 decomposing to give us NO2 and NO3. We have the reverse of that reaction, which NO2 and NO3 recombine to give us N2O5. And we have 2 additional steps where NO2 and NO3 react to give us various species, and a final step where NO3 and NO react to give us 2 equivalents of NO2. So these are the 4 steps involved in this reaction mechanism. So this is an example of a complex reaction, which we define as a reaction that occurs in 2 or more elementary steps. And what we see here is that in addition to the reactant N2O5, in the overall reaction products, NO2 and O2, there are 2 other species that appear in this mechanism, both NO3 as well as NO. And these are not found in the overall reaction, so we refer to these species as reaction intermediates. So what we're going to do now is we're going to use the steady state approximation to determine a rate law expression for the decomposition of N2O5 using the mechanism that we just proposed. And what we want to assess is whether or not the order of the reaction predicted by the above mechanism agrees with the experimentally determined order, which was first order in N2O5. So when we carry out these particular types of questions, I'd like to start off by stating what the net rate of change is for the individual species with respect to the overall reaction. And so, although we are solving for the decomposition of N2O5 with time, it's important to set up this expression such that once we derive the rate law expression for N2O5, we can also relate that to NO2, O2, or the overall rate of the reaction. So the first step, nonetheless, is to focus in on the decomposition of N2O5. And so equation 1 is going to express the formation of N2O5 with respect to that reaction mechanism. And I often recommend that we solve for the formation of species of interest because I'm often concerned that this negative sign that we'd have to include for the decomposition may get lost somewhat in our derivation. So we can always fix that later on. So I always recommend that we start by solving for the formation with respect to a species. So if we do that, N2O5, looking at the net rate of change during the course of this mechanism, in the first step, it's being consumed, and so we're going to show a minus K1 multiplied by the concentration of N2O5. But in the second step, which is really the reverse, it's an equilibrium, reverse of that first step, we see it being reformed at the rate constant K minus 1 and depend upon the concentrations of NO2 and NO3. Now, if these two terms only contained reactants and products found in the overall reaction, then we would be done of this particular question. We would have our rate law expression. But as you can see, in the second term, we have a species that's not found in the overall reaction. NO3 as well as nitrogen oxide, NO, these are species known as reaction intermediates. And so we must also solve for this particular concentration in order to solve for the formation or decomposition of N2O5. So that requires that we continue by setting up an expression that relates the change in the concentration of NO3 with respect to our mechanism. Now, NO3 is found in each of the 4 steps in our proposed complex reaction mechanism. So we have 4 terms associated with that. So we have it being formed in the first step with a rate constant K1 and dependent upon the concentration of N2O5. It's being consumed in the second step with a rate constant K minus 1 and dependent upon the concentration of NO2 and itself, NO3. In the third step, it's also consumed with a rate constant K2 with the concentration of NO2 and NO3 being important. And in the fourth step, NO3 reacts with NO. It's also being consumed in that step with a rate constant K3 as NO2 is being formed in that fourth step. Now again, if these terms only contained reactants, products, and the species NO3, which we're trying to solve for, then we could stop. But we see that NO appears in this fourth term. So it being another reaction intermediate and not wanting to have reaction intermediates in our overall rate law expression, we're going to have to set up a third expression for the net rate of change of NO. Now, the species nitric oxide is found in 2 steps. It's found in the third and fourth step. It's formed with a rate constant K2, dependent upon the concentrations of NO2 and NO3. And then in that final step, it reacts with NO3 with a rate constant K3. So here's that term here, a minus K3 times the concentration of NO and NO3. So we now have the 3 expressions that we need in order to solve for the rate law expression with respect to the decomposition of N2O5. So let's see how we deal with this information. How do we proceed by using the steady state approximation? We haven't used the approximation yet, but we're going to right now. So we need to solve for the concentrations of NO3 and NO. And in order to do that, we're going to equate their time derivatives, their net rate of change, to 0. And that is the steady state approximation, where we state that during the course of the reaction, the net rate of change of the intermediate concentration will remain constant. So it'll be equal to 0. As well, we're also stating that the intermediate concentrations are quite low relative to the concentration of reactants and products at any one point in time. And we discussed that previously, and we said that although the steady state approximation is an approximation and not an exact solution to how intermediates are formed and decaying to product during the course of a reaction, it is a fairly good assumption which allows us to assess the overall rate law expression quite conveniently. So after applying the steady state approximation, we have to explicitly state this every time we carry out this particular type of question. We have to state it. Once we state it, we can then use the approximation to solve for the concentration of the reaction intermediates. So if we rearrange 3 now, we can do that because we've equated expression 3 to 0. We can solve for the concentration of NO. And in doing so, we end up with this quotient. And you can see that we can simplify this quotient slightly by canceling out the concentration with respect to NO3 in the numerator and denominator. And so this leads us with a new expression, expression 4, which is a solution for the concentration of NO. Once we have that particular equality, we can substitute this equality into expression 2, where NO is present. And so in doing so, not only are we equating expression 2 to 0, because we stated that in our steady state approximation, we're now substituting in for NO with the K2, K3 times the concentration of NO2 term. You can see right away we have simplification again, where K3s will cancel out. And it's important to carry out these simplifications as we go so that we don't have a lot of simplification to do at any one endpoint, that we can carry out these simplifications as we go along. So now we have our slightly simplified expression. What we're going to do now is we're going to bring all the terms that contain negative signs to the right-hand side, and we're going to leave this positive term on the left. In doing so, you see we have K1 N2O5 now equal to K minus 1 NO2 NO3 plus 2K2 N2O3, because we had two identical terms that came out of our simplification. In the next step, we're going to factor out NO2, NO3 and bring all the rate constants out front in a bracket. And so we're left with K minus 1 plus 2K2 multiplied by those concentrations. And finally, we can solve for NO3 by dividing both sides by the bracketed term and NO2. And so we're left with the concentration of NO3 now expressed as a quotient in terms of both a reactant and a product. And so we don't need to carry out any further substitutions in this particular solution. Now we can take the concentration of NO3 and its solution and substitute it into expression 1, which was for the formation of N2O5. This is what we end up with. And you can see here again, we can simplify it slightly by canceling out the concentration term with respect to NO2. Now this may look like a final solution, but we're not quite there yet. We still don't clearly see this first order dependence with respect to N2O5. We do in two different terms, but we should look at the summation of this before making that conclusion. So, as typical with these types of questions, we're going to look for a common denominator when we add or subtract two different terms. So the common denominator will be K minus 1 plus 2K2, and that will be multiplied by the first term in order to get a single quotient. So we have to multiply our common denominator by the first term, we'll multiply that through, so we end up with a minus K minus 1 K1 N2O5 shown here, minus a 2 K1 K2 N2O5, and then we carry this third term down. We look for like terms in any kind of simplification, and luckily we see that we have identical terms but with opposite signs, the first and third term, and so they're going to cancel out as well. And so we're left with the following solution, where we have a minus 2 K1 K2 over the sum of K minus 1 plus 2 K2. And this is all multiplied by the concentration of N2O5. Now we're starting to see, or very close to seeing, this first order dependence. Now, the original question asked us to solve for the rate law expression with respect to the decomposition of N2O5. So in order to show that, it's at this point that we would multiply both sides by -1, such that we're looking at the decomposition of N2O5. And in doing so, we simply will make this -2 K1, K2 numerator term as a positive. And so this ends up being our final solution for this question. We now have a rate law expression that describes the decomposition of N2O5 during the course of this reaction. And we can, if we wish, to somewhat package this as a K effective if we wish. So we could simply make this term K effective, because when we carry out this experiment and when we plot our data, as you know, the slope in this particular instance will be equal to minus K effective. And so K effective is not equal to a single rate constant, but for this complex reaction mechanism, our K effective is equal to a complex quotient of rate constants. So this is another way in which we could describe the decomposition of N2O5. Now, one last thing that I'll point out is that on occasion, you may be asked to derive or determine a rate law expression for the overall rate of the reaction. And in that instance, you have to choose either a reactant or a product to initially follow using the steady state approximation, and then we equate that back to the overall rate of the reaction using that initial equality. So as we did in this example, we started off by expressing the rate of the reaction in terms of both reactants and products, and this was what we came up with for N2O5. And so now if we want to solve for the rate of the reaction, then we will take our solution for the formation of N2O5 and substitute that in for this particular expression. And so you can see what happens is that we have a sign change, as well as we're going to see the canceling of this constant 2. So the overall rate of the reaction is going to be equal to this quotient of rate constants multiplied by the concentration of N2O5 to the power of 1. And similarly, we could express this as a K effective, this entire quotient, and define it clearly as shown. So this too can be a useful way to describe the rate law expression for a particular reaction. You may want to express it in terms of the overall rate of the reaction and not with respect to a single species. So the resulting rate law expression for the decomposition of N2O5 demonstrates that the mechanism is consistent with the experimentally observed first order dependence on N2O5. However, the consistency of a reaction mechanism with the experimental order dependence of the reaction is not proof that the mechanism is absolutely correct, but instead demonstrates that the mechanism is consistent with the experimentally determined order dependence. It is quite possible that an alternative mechanism could be constructed that is also consistent with the experimental order dependence. Nonetheless, this example illustrates how reaction mechanisms are used to explain the order dependence of a reaction rate. In addition, the mechanisms of many complex reactions can be decomposed into a series of elementary reaction steps. And just to reiterate this particular point is that we don't prove anything in science, and this is especially true for the development of rate law expressions, is that when we're examining reactions and trying to understand the details of those reactions, we make proposals and we collect experimental evidence to support or refute those proposals. And although in this case we see that consistency between the proposal and what we observe experimentally, it's always important to recognize that with further examination, further study, we may uncover information that we didn't initially have, which may change slightly our proposal or may drastically change our conclusions. So it's important to recognize that we don't prove things in science, we provide supporting evidence. We set up hypotheses, hypothesis-driven scientific discovery, and we collect experimental data to support that hypothesis or refute it. So let's look at one more example of how we can apply the steady state approximation to help us develop, determine, assess rate law expression for a complex reaction mechanism. So in this example, we're going to look at the decomposition of ozone. So the overall reaction is 2 equivalents of ozone reacting to give us 3 equivalents of O2. And this overall reaction is based on the following mechanism, where we have 3 steps: ozone decomposing to give us O2 and atomic oxygen, the reverse of that reaction, which is O2 and atomic oxygen reacting to give us ozone, and a third step, which involves atomic oxygen with ozone to give us 2 equivalents of O2. So let's look at the steady state approximation and come up with a rate law expression based on this complex reaction mechanism. So as we saw in the previous example, we first start by equating the overall rate of the reaction with respect to the individual species in that reaction. And that way, once we solve for the rate of decomposition of ozone, we can then relate that to the formation of oxygen or the overall rate of the reaction. Secondly, we start by solving for the net rate of change of ozone. Again, we're going to look at formation, even though we're after decomposition. That's something we can play with the signs later, but this way we're not going to lose that negative sign during the course of our derivation. So you can see that we're going to have 3 terms in this particular expression. That's because ozone is found in each of the 3 steps of our reaction mechanism. In the first step, it is decomposing with a rate constant K1 and dependent upon the concentration of ozone. In the second step, it is formed with a rate constant K-1 dependent upon the concentration of O2 and atomic oxygen. And in the third step, it is consumed with a rate constant K2 dependent upon the concentration of atomic oxygen and itself. Now again, we look at this particular expression and we see that we have a reaction intermediate. We have atomic oxygen, which is not found in the overall reaction. We have that in this expression. So we need to solve for that particular concentration, and this is where the steady state approximation comes in quite handy. So we have equation 2. We're going to set up solving for the net rate of change of that intermediate species, atomic oxygen, and it too is found in all 3 steps. And so it's formed in the first step, rate constant K1 times concentration of O3, consumed in the second step with a rate constant K-1, concentration of O2 and itself, and is also consumed in the third step with a rate constant K2, dependent upon, of course, its concentration of O3 and itself. So we're applying the steady state approximation to the reaction intermediates. That's where we can, in fact, simplify our derivation, is by equating the net rate of change of the intermediate to 0. In doing so, we can equate equation 2 to 0 and rearrange it and solve for the atomic oxygen concentration. And then in that way, we can substitute it back into expression 1. So that's the overall procedure that we're after. So you can see that once we apply the steady state approximation, we can rearrange expression 2 and come up with expression 3 for the concentration of atomic oxygen. So we have this quotient representing that particular concentration. So once we have that particular concentration of oxygen expressed in terms of various terms, we can now substitute that into our original expression 1, which was for the formation of ozone. You can see that we've carried out that substitution in those second and third terms. There's no simplification that we can carry out right away, but we're going to multiply what's found outside the brackets with the numerator inside the brackets. And so we're left with these three terms. Make note that we have a K2 times K1 O3 and an O3 on the end of that particular expression. So that gives us this numerator. And then if we multiply this by this, it gives us this numerator. Now, like we saw in the previous question, we have a common denominator in two of the three terms, and that will be the common denominator that we'll use to bring these three terms to a single quotient. In doing so, we're going to multiply the common denominator by this first term, and that's shown here. And then we're going to multiply through in the next step. So we're left with a minus k minus 1 k1 O2 O3 minus k1 k2 O3 to the square. And then these remaining terms carry down. Now we can see that we have some simplification. We have identical terms, the first and third terms. These are identical, but of opposite sign. And then the second and the fourth terms, these are identical, but of equivalent sign. And so we see these will cancel out, and we'll add these two together. So we end up with an overall expression for the formation of ozone, which is a quotient of a minus 2 K1, K2 concentration of ozone to the square all over that common denominator. And this is very close to our solution, except we were asked to solve for the decomposition of ozone. So therefore, we can multiply both sides by -1, and we're left with our final solution of a 2K1, K2 concentration of ozone to the square over K minus 1 times the concentration of O2 plus K2 times the concentration of O3. And so this would be our final solution that we were after for this particular question. This is the rate law expression for the decomposition of ozone. Now we could go one step further if we wanted to solve for the rate law expression that represents the overall reaction. Then we need to use this particular equality and substitute into it. And that's what we're showing here, is that we can take our solution from the bottom of the previous slide. We can substitute that in as shown in brackets. That's going to result in cancellation of these negative signs and 2 in the numerator and denominator. So again, using the steady state approximation, we've been able to determine a rate law expression for the decomposition of ozone, as well as shown here for the overall reaction. And the steady state approximation basically allows us to solve for the concentration of reaction intermediates. And by doing so, we can take those solutions and incorporate them into the expressions for the species of interest in the overall reaction. Now, one last thing I'd like to discuss is that in this particular question, we were asked to solve for the decomposition of ozone. And I just showed you in the previous slide that using that information, we can come up with a rate law expression for the overall reaction. We could have solved for the formation of oxygen to get to that same point. And so I want to show that this is self-consistent, that we could solve for decomposition of a reactant or the formation of a product, and that will lead us to the same final rate law expression for the overall reaction. So in order to do that, we need to first solve for the formation of O2. And like we did for previous species, we end up with a number of terms where O2 is present in our complex reaction mechanism. So it is formed in the first step, dependent upon the rate constant K1 and the concentration of ozone. It's consumed in the second step, K minus 1, dependent upon O2 and atomic oxygen. And in the third step, it's actually formed twofold, that This is an elementary reaction step, but every time atomic oxygen and ozone reacts to give you oxygen, it actually gives you 2 equivalents of oxygen. So 2 moles of oxygen are formed in each elementary step. So if we go back to the mechanism, we see that we have 2 equivalents of O2 being formed in that step. So we need to multiply the rate constant by 2 to represent that in the formation of O2, we're forming 2 equivalents of O2 in that single elementary step. So we have a 2K2 times the concentration of atomic oxygen in ozone. Now we can substitute in for atomic oxygen using the expression that we determined after applying the steady state approximation. So we can substitute 3 into this new expression 4, and we end up with the following. And similarly, we can't do any cancellations after that first substitution. And similarly, we're going to end up with the exact same common denominator in this particular derivation. And so we're going to carry out the same process. We're going to take the common denominator, multiply it by the first term. Then we're going to multiply it through to give us 4 terms. And like we saw previously, we're going to have some cancellations. We're going to have cancellation of these 2 terms and summation of this term and this term. And so we end up with the formation of O2 with time being equal to 3K1, K2 ozone concentration to the square over the same common denominator. And again, if we want to solve for the overall rate expression, or the rate expression for the overall reaction, we would carry out a similar substitution where this entire term would be substituted here. That's going to result in the cancellation of this constant 3. And this is our final solution from a different perspective, or by starting off following the formation of O2 as opposed to the decomposition of ozone. And this is the exact same solution that we obtained in the previous example. So again, here's that same solution when we approached it from a decomposition of the reactant perspective. And if the system, the reaction mechanism is self-consistent, we should end up with the same result, whether we follow the reactant or the product. So if you have any questions about the steady state approximation and how it's used to determine a rate law expression for a complex reaction mechanism, by all means, send me an email. Thank you.